I'm so glad you found your way back. You're resting with Science Blanket, your quiet sanctuary for the curious mind. Have you ever watched a single drop of ink vanish into a glass of water and felt like you were witnessing a slow-motion dream? Tonight, we're wrapping ourselves in the science of the inevitable, specifically, the steady, one-way journey of time. We often think of it as a ticking clock, but it is actually the ghost of entropy, trillions of particles moving from order into a delicate, chaotic balance with the void. From the high, fleeting moments of the present that feel like pulled silk to the heavy, silent memories of the past that bring the weight of a lifetime, the forward flow of time is the visible signature of the universe's invisible expansion. As we begin, imagine yourself drifting on a quiet river that only flows in one direction, feeling as weightless and surrendered as the current itself. You don't need to understand the physics of thermodynamics or the names of the temporal dimensions tonight. Just let the slow, rhythmic march of the seconds tuck you in. If this blanket of the ages helps you find rest, I'd love for you to subscribe and join our community of sleepy explorers. Now, take a slow, deep breath. Feel your lungs expand and then empty, as steady as a pendulum. Let the weight of your day drift behind you into the quiet shadows of the past. Relax your jaw, let your shoulders drop, and sink into the softness of your bed. Let's explore the quiet wonders of why time only moves forward together. There's something deeply unsettling about breaking a glass. You watch it slip from your fingers, hear that sharp crack as it meets the floor, and suddenly what was whole becomes scattered across the tiles in 1,000 glittering pieces. You might stand there for a moment, staring at the chaos, and somewhere in the back of your mind a thought emerges. This can't be undone. Not really. You could gather the shards, carefully align each fragment, apply the strongest adhesive known to science, but it would never be the same glass. It would be a repaired glass, a broken thing made whole again through effort and energy and intervention. What you would never see, not in a trillion years of waiting, is those scattered pieces suddenly leaping up from the floor, racing backward through the air, and reforming themselves into the intact glass that once rested safely in your hand. This isn't just unlikely. It's a window into something profound about the nature of reality itself. The universe has a preference, though preference might be too gentle a word for something so absolute. It has a law, carved deep into the fabric of existence, and that law tells us that disorder always wins. We call this the Second Law of Thermodynamics, and it states with perfect clarity that entropy in an isolated system never decreases. Entropy, that measure of disorder and randomness, can stay the same or it can increase, but it cannot go backward. And in that simple statement lies the answer to one of the most fundamental questions we can ask. Why does time move forward? Why do we remember yesterday but not tomorrow? Why can't we unbreak the glass? Think about an ice cube melting in a glass of water. You've seen this countless times. Watch the solid slowly dissolve into liquid, the cold spreading through the water until everything reaches the same unremarkable temperature. This is an irreversible process, one of countless examples that surround us every moment of every day. The ice melts. The heat spreads. The difference disappears. And you could wait forever, staring at that glass of lukewarm water, and you would never see the reverse happen spontaneously. You would never see the molecules suddenly organize themselves, the heat gathering itself back into concentrated form, the water crystallizing back into a perfect cube of ice. Not because it violates any deep law of physics at the microscopic level, but because it requires such an astronomically precise arrangement of particles that the probability becomes effectively zero. Or consider opening a bottle of perfume in the corner of a room. The scent molecules rush out, spreading and dispersing, carried by the random motion of air molecules until eventually the fragrance reaches every corner of the space. This happens naturally, inevitably, without any effort on your part. But the reverse, all those perfume molecules spontaneously gathering themselves back together and returning to the bottle, leaving the air fresh and unscented, this never happens. The molecules spread from order to disorder, from concentration to diffusion, and in doing so they're following the arrow that points in only one direction. Here's where things become strange and beautiful. If you could shrink down and watch individual molecules, individual particles, the fundamental interactions between them, you'd find something surprising. The basic laws of physics that govern these tiny interactions don't actually care about time's direction. An electron orbiting an atom, two particles colliding and bouncing apart, these processes are time-symmetric. If you filmed them and played the film backward, you wouldn't see anything that violates the fundamental laws of nature. At the microscopic level, time could run either way. Physics at its most basic doesn't prefer forward over backward. And yet, zoom out to our scale, to the world of ice cubes and broken glasses and spreading perfume, and suddenly time has a direction. Suddenly, the universe has a preference. The microscopic permits both directions, but the macroscopic allows only one. The resolution to this paradox lies in numbers, in probability, in the sheer overwhelming odds that emerge when you're dealing with countless trillions of particles rather than just one or two. The universe began in a very special state, a state of extraordinarily low entropy, everything compressed and organized in ways that seem almost impossibly unlikely. And from that low entropy beginning, everything that has happened since has been a journey toward higher entropy, toward greater disorder, toward a future that is always more random than the past. This isn't because disorder is somehow more natural than order in any absolute sense. It's because there are vastly, monumentally, incomprehensibly more ways for things to be disordered than to be ordered. Imagine a perfectly organized deck of cards, arranged by suit and rank, everything in its proper place. There's exactly one way to achieve that specific perfect order. But shuffle the deck, and there are more than 80 unvigintillion different arrangements it could end up in. Most of those arrangements look random to us, look disordered, because order is rare and disorder is common. The universe isn't choosing disorder over order out of some cosmic preference. It's simply moving through the space of possible states, and that space contains overwhelmingly more disordered states than ordered ones. The future vastly outnumbers the past in terms of possible configurations. Forward evolution, the progression toward higher entropy, is overwhelmingly more probable than any exact reversal back to a previous low-entropy state. This is why you remember yesterday but not tomorrow. Memory itself is a physical process, encoded in the structure of neurons in your brain, and the formation of a memory increases entropy. When you experience something and form a memory of it, you're creating a physical record, a pattern in matter, and that creation is an irreversible thermodynamic process. Your memories point backward because they're records of past events, traces left behind by entropy's increase. You remember the glass before it broke because that earlier, more ordered state left its mark on your brain. The arrow of your psychological experience, your sense of past and future, is intimately tied to the thermodynamic arrow that points from low entropy to high. The universe itself seems to share this directionality, this sense of moving forward through time. We observe that space itself is expanding, galaxies rushing away from each other, the whole cosmos growing larger and less dense with each passing moment. This cosmological arrow of time, the direction in which the universe expands, aligns perfectly with the thermodynamic arrow. Both point the same way, from the dense, hot, low-entropy state of the early universe toward a future of greater space, lower density, and higher entropy. Whether these arrows are fundamentally the same thing or merely correlated remains one of the deep questions, but their alignment gives time its character, its forward flow, its relentless progression from what was toward what will be. And if you let this process continue, if you imagine the universe running forward for unimaginable spans of time, you eventually reach a strange and quiet end. If entropy continues to increase until it reaches its maximum possible value, something remarkable happens. Or rather, something remarkable stops happening. Change requires differences, gradients, concentrations of energy or order that can flow from one state to another. In a maximum entropy universe, all these differences would be smoothed away. Everything would reach the same temperature, the same density, the same unremarkable equilibrium. And in such a state, macroscopic change would cease. Nothing interesting would happen because there would be no energy gradients left to make things happen. Time, in any meaningful sense, would lose its direction because there would be no arrow of change to follow. The clock would still tick in some abstract sense, but there would be nothing to mark one moment as different from the next. The universe would reach a kind of stillness, a heat death where time's arrow, having completed its flight, finally comes to rest in a sea of perfect, meaningless disorder. We live in a universe where the impossible and the merely improbable occupy very different territories. Somewhere in the vast landscape of physical law, there exists the theoretical possibility of watching spilled coffee leap back into your cup, of seeing smoke flow backward into a candle flame, of witnessing any of the irreversible processes we take for granted simply running in reverse. The equations don't forbid it. The fundamental laws of physics, written in their purest mathematical form, leave room for time to flow either way. But between theoretical possibility and practical reality lies a chasm so vast that it might as well be the difference between something that could happen and something that never will. The odds against a time-reverse process occurring spontaneously are so astronomically, so incomprehensibly small that you could wait longer than the current age of the universe, multiplied by itself countless times over, and still never witness such an event. This brings us back to a moment of extraordinary significance, to the very beginning of everything we can observe and measure. The Big Bang wasn't just the start of space expanding or matter coming into being. It was the establishment of a condition so special, so remarkably ordered, that everything since has been defined by our departure from it. The universe began in a state of incredibly low entropy, all its energy and matter compressed into a configuration that represented profound order despite the chaos and heat. And it's this low-entropy starting point that defines what we mean when we say time moves forward. Forward is simply the direction away from that initial state. Forward is the direction in which entropy grows. If you could somehow reverse the universe's expansion, run everything backward toward that initial moment, you'd be moving against the thermodynamic arrow, traveling from high entropy to low, and that direction we would naturally call backward through time, toward the past, toward the beginning. The Big Bang didn't just create space and time. It created the distinction between past and future. Yet even here, in this seemingly absolute law of time's direction, nature preserves a few surprises. tiny exceptions that remind us how subtle and strange reality can be at its deepest levels. When physicists study certain subatomic particles and their decay processes, they find something unexpected. Most particle interactions are essentially symmetric under time reversal. Run them backward and they still obey the fundamental laws. But a few specific types of particle decay show tiny, almost imperceptible violations of this symmetry. These violations are extraordinarily small, buried deep in the quantum realm, but they're real and measurable. Certain particles decay in ways that would look slightly different if you could reverse time's arrow. These asymmetries don't overturn the thermodynamic arrow. They don't allow us to reverse entropy's growth. But they hint that at the most fundamental level, time's direction might be woven into the basic fabric of physical law in ways even more profound than thermodynamics alone suggests. The quantum world, that strange realm of probability and uncertainty that underlies everything, offers its own peculiar relationship with time's arrow. Quantum mechanics allows for fluctuations, temporary backward movements, microscopic violations of the steady march toward disorder. A small system, isolated and observed carefully, might spontaneously decrease in entropy for a brief moment. These quantum fluctuations are real, measurable, and don't violate any fundamental laws. But they're always temporary, always local, always overwhelmed by the larger thermodynamic trend. Think of them as tiny eddies in a mighty river. The water might swirl backward locally, might move upstream for a moment in a small pocket, but the river as a whole still flows inexorably in one direction. These quantum fluctuations can't be harnessed to reverse time or decrease the total entropy of any meaningful system. They're permitted variations within the rules, not violations of the overall pattern. The universe allows microscopic backward movements while preserving the forward march of time on every scale that matters to our experience. Einstein showed us that space and time aren't separate things but aspects of a unified whole, a four-dimensional fabric we call space-time. In this geometric picture, time is sometimes called the fourth dimension, placed mathematically alongside the three dimensions of space. You can move freely forward and backward in space, left and right, up and down. These spatial dimensions are symmetric. There's nothing in the structure of space itself that privileges north over south or east over west. And yet time, despite being woven together with space in the geometry of space-time, behaves completely differently. You can't move backward through time the way you move backward through space. You can't turn around and walk into yesterday. The growth of entropy singles out a temporal direction in a way that has no parallel in the spatial dimensions. Space-time might be unified, but time remains special, marked by an asymmetry that emerges from the physical conditions and processes that unfold within that geometric framework. Einstein's relativity also revealed that time is flexible in ways that would have seemed impossible to earlier generations. Move fast enough, approach the speed of light, and time slows down for you relative to someone at rest. Fall deep into a gravitational field, near the event horizon of a black hole perhaps, and time dilates, stretching and slowing compared to someone far away in weaker gravity. These effects are real and measurable. Astronauts on the International Space Station age ever so slightly slower than people on Earth's surface. Precise atomic clocks flown on airplanes show measurable differences from identical clocks left on the ground. Time is not absolute. Different observers, moving at different speeds or experiencing different gravitational fields, will measure time passing at different rates. Their clocks tick at different speeds. But notice what doesn't happen. No matter how fast you travel, no matter how deep you fall into a gravitational well, your clock never runs backward. Time might slow down, might nearly stop in extreme conditions, but it never reverses. The rate of time's passage is flexible, but its direction is not. We've built clocks of extraordinary precision, devices that can measure time's passage to billionths of a second or better. We've placed these clocks in satellites, in high-speed aircraft, in deep mines, in laboratories around the world. We've subjected them to acceleration, to gravity, to electromagnetic fields, to every condition we can create. And in every single test, without exception, these clocks record time increasing. They might tick faster or slower depending on their conditions, but they all agree on the direction. They all move forward. Never has any clock, no matter how sensitive or how carefully monitored, shown time running backward. This consistent testimony from every measurement ever made isn't just experimental confirmation of theory. It's a profound statement about the nature of reality. Time's forward direction isn't a human convention or a trick of perception. It's written into the behavior of physical systems at every scale we can measure. Similarly, in all our observations of natural processes, from the grandest cosmic events to the smallest laboratory experiments, we've never witnessed any process that reduces the total entropy of the universe. Local entropy can decrease, certainly. A refrigerator creates order locally, cooling its interior and organizing heat energy. But it does so by increasing entropy elsewhere, by dumping heat into the surrounding room, by consuming electricity that came from power plants that increased entropy elsewhere. When you account for the total system, including everything the refrigerator affects, entropy goes up. Life itself is often cited as something that decreases entropy, taking disordered nutrients and building ordered structures, complex organisms that seem to defy the slide toward chaos. But living things are not isolated systems. They consume energy, usually from the sun either directly or indirectly through food chains, and they return heat and waste to the environment. Account for the whole process, the entire thermodynamic system, and life increases entropy just like everything else. The second law has never been violated in any observation. Not once. Not ever. This leads to a curious asymmetry in the information required to describe processes depending on their direction. If you want to predict the forward evolution of a system, you need to know its current state and the laws that govern its behavior. That's challenging but manageable. But if you want to reverse a complex system, to take a scrambled configuration and run it backward to its ordered past, you need vastly more information. You need to know the precise position and velocity of every particle, every quantum state, every detail down to the finest level. The information requirements for reversal grow exponentially with system complexity. For any macroscopic system, containing more particles than you could count in a lifetime, the information needed to specify a reversal becomes effectively infinite. This isn't just a practical limitation of our measuring devices. It's a fundamental statement about the asymmetry of time. Forward evolution loses information, allows many initial states to lead to similar final states, permits the details to blur into thermodynamic averages. Backward evolution would require reconstructing all that lost information, recovering every detail that the forward process erased. The universe remembers the future only vaguely but would need to remember the past perfectly to reverse its journey. And so we return to a central mystery. Space offers you freedom of movement in all directions. You can go north or south with equal ease. There's no cosmic arrow pointing north, no law of nature that makes northward travel fundamentally different from southward travel. But time is different. Time has an arrow that emerges not from the geometry of space-time itself, but from the physical conditions within it, from the universe's low-entropy beginning and the inexorable growth of disorder that followed. The asymmetry of time isn't built into the fabric of space-time in the way that spatial dimensions are. It's a contingent fact about our particular universe, about the specific state it started in and the thermodynamic laws that govern its evolution. In a different universe, with a different initial state, time might not have a direction, or it might have a different one. But in our universe, with our history, with our Big Bang beginning, time points unmistakably forward, and everything we experience, from memory to causation to the breaking of glass, follows that arrow toward an ever more disordered future. Every culture has imagined traveling to the past, visiting yesterday or last century or the age of dinosaurs, walking through history as easily as walking through a doorway. It's one of humanity's most persistent fantasies, woven through countless stories and films and dreams. And yet every serious attempt to find a path backward through time, every equation explored, every theoretical framework examined, runs into the same fundamental barrier. There is no accepted theory of physics that allows macroscopic travel to the past. Not in general relativity, despite its allowance for strange space-time geometries. Not in quantum mechanics, despite its probabilistic strangeness. Not in any combination or extension of our current understanding. You can slow time down, experience it differently, measure it at different rates, but you cannot reverse your journey through it. You cannot go back. The mathematics might permit certain exotic solutions, theoretical spacetimes with closed time-like curves where the geometry loops back on itself, but these solutions require conditions so extreme, so physically unrealistic, that they remain firmly in the realm of mathematical curiosities rather than practical possibilities. The universe, it seems, guards the past jealously, keeping it sealed behind a barrier that no amount of energy or ingenuity can breach. The reason for this prohibition becomes clearer when you understand where time's arrow truly comes from. It's not imposed by some arbitrary cosmic rule. It emerges naturally, inevitably, from a single remarkable fact about the universe's beginning. Approximately 13.8 billion years ago, everything we can observe existed in a state of extraordinarily low entropy. This wasn't just hot and dense. Many hot, dense configurations would have very high entropy. No, the early universe was special, organized in a way that contained vast potential for change and evolution. All the energy and matter that would eventually form galaxies and stars and planets, and you existed in a configuration so improbable, so precisely arranged, that we still don't fully understand why it began that way. But it did. And from that moment forward, everything that happened, every particle interaction, every force exchange, every process at every scale, moved away from that special initial state toward more probable, more disordered configurations. Time's arrow emerges from this history. Forward is simply the direction leading away from the Big Bang's low-entropy beginning. Backward would mean returning to that increasingly improbable past, and the universe doesn't allow such journeys. Statistical mechanics, the mathematical framework that connects the microscopic world of particles to the macroscopic world of thermodynamics, provides the mathematical foundation for understanding this directionality. When you have a system with countless particles, each moving and interacting according to basic physical laws, the system will evolve along the most probable paths through its space of possible states. And those probable paths always lead from less likely configurations to more likely ones, from lower entropy to higher entropy. It's not that each individual particle knows to move toward disorder. It's that when you have enormous numbers of particles, the collective behavior overwhelmingly favors certain outcomes simply because there are vastly more ways to achieve those outcomes. Forward evolution follows the gradient of increasing probability, always moving toward futures that are more typical, more common, more representative of the vast majority of possible states the system could occupy. To reverse this process, to send a macroscopic system backward through time, would require something that statistical mechanics tells us is effectively impossible. You would need coordinated particle behavior on an unimaginable scale. Every atom, every molecule, every elementary particle would need to move in precisely orchestrated ways, their velocities and positions aligned with such exactitude that they collectively retrace their paths backward through increasingly improbable states. The odds against this happening spontaneously are so small that expressing them in any meaningful way becomes almost pointless. Imagine not just shuffling a deck back to its original order by chance, but shuffling every deck of cards that ever existed, all simultaneously reverting to the same specific arrangement, and you're still not remotely close to the improbability of macroscopic time reversal. The universe contains something like 10 to the 80 particles in the observable region. Coordinating their behavior to reverse entropy's growth would require overcoming odds that dwarf even these cosmic numbers. And yet, hidden in the quantum realm, in the behavior of fundamental particles, there exists another kind of temporal asymmetry, one that operates independently of thermodynamics. When physicists study something called CP violation, a subtle asymmetry in how certain particles behave compared to their antiparticles, they find a microscopic arrow of time built into the fundamental laws. CP stands for charge conjugation and parity, technical operations that essentially ask what happens if you swap particles for antiparticles and flip spatial coordinates like looking in a mirror. For most interactions, these symmetries hold perfectly. But for certain rare processes involving specific particles, mainly in the weak nuclear force, these symmetries are slightly violated. And when CP is violated, time reversal symmetry is also violated through a deep connection in quantum field theory. This means that even at the most fundamental level, even in the realm of individual particles where thermodynamics doesn't apply, time has a preferred direction. This microscopic arrow doesn't determine the everyday flow of time we experience, but it suggests that temporal asymmetry is woven into nature at multiple levels, from the quantum to the thermodynamic. The philosopher and physicist Ludwig Boltzmann, who helped establish statistical mechanics, pondered a strange possibility that now bears his name. If the universe has existed forever, fluctuating randomly through all possible states, then eventually, by pure chance, a low-entropy configuration would arise from the chaos. And within that fluctuation, purely by accident, there might form something as organized as a human brain, complete with false memories of a past that never existed. This so-called Boltzmann brain scenario is deeply disturbing because it suggests that any given conscious observer is more likely to be a random fluctuation than a genuine product of a long evolutionary history. The resolution to this paradox reinforces why the universe's low-entropy beginning is so crucial. If time's arrow emerges from a genuine low-entropy initial condition rather than from random fluctuations, then we can trust that our memories reflect real history, that the world around us has genuine structure and continuity. The low-entropy origin isn't just necessary for time to have a direction. It's necessary for our existence and experiences to be meaningful rather than momentary statistical accidents in an eternal chaos. Consider how energy radiates outward from sources. Drop a stone in a pond and watch the ripples spread outward in expanding circles. Turn on a light and watch illumination flow outward from the bulb in all directions. Electromagnetic radiation, whether light or radio waves or any other form, propagates outward from its source, not inward toward it. This defines what physicists call the radiative arrow of time. We never see ripples spontaneously converging from all directions to form a perfectly organized pattern at a point, then launching a stone upward into someone's hand. We never see light rays coming from infinity to converge perfectly on a bulb, which then absorbs them. The outward flow of radiation, the expansion of disturbances from their sources, is another manifestation of time's directionality. It's connected to thermodynamics, to entropy growth, to the spreading of energy and information from concentrated sources into the wider universe. And it's entirely consistent with the other arrows we've discussed, all pointing the same direction, all following the same cosmic current from past to future. Quantum mechanics introduces its own form of irreversibility through the measurement process. Before you measure a quantum system, it exists in a superposition of possible states, each with its own probability. But the instant you perform a measurement, the superposition collapses. The system selects one outcome, and that selection is irreversible. You can't unmeasure something, can't put the quantum system back into its previous superposition of possibilities. This collapse, this transition from possibility to actuality, happens only in one direction. It's another arrow pointing forward, another process that distinguishes past from future. Whether this collapse is fundamental or emerges from decoherence and interaction with the environment remains debated, but either way, the practical result is the same. Quantum measurements introduce irreversible outcome selection, adding another layer to time's one-way nature. Black holes, those regions where gravity becomes so intense that nothing can escape, enforce causality in the most dramatic possible way. Once something crosses the event horizon, the boundary of a black hole, it cannot return. Every path forward in time leads inward, toward the singularity at the black hole's center. No amount of thrust, no velocity, not even light itself can reverse this journey. The black hole's horizon creates a one-way membrane in spacetime, a surface that permits passage in only one temporal direction. This isn't just a practical limitation of insufficient power. It's built into the causal structure of spacetime itself. Once you've crossed that threshold, your past lies outside the horizon and your future lies inward, and no possible action can change that fact. Black holes are time's arrow made visible in the geometry of space itself, regions where forward and backward are as absolutely defined as they are anywhere in the universe. Finally, consider how structure forms in the universe. The early universe was remarkably smooth, with only tiny density variations across vast regions. But gravity amplifies differences. Slightly denser regions attracted more matter, becoming denser still, eventually forming galaxies, stars, and all the intricate structures we observe today. This process of structure formation increases gravitational entropy. The smooth early universe had low gravitational entropy despite its high temperature. As structure formed, as matter clumped together into concentrated objects separated by vast voids, gravitational entropy grew. A universe with galaxies, with black holes, with all the complexity of cosmic structure, has higher gravitational entropy than a smooth universe of the same total energy. This provides yet another arrow of time, a gravitational arrow pointing from smooth to structured, from a universe of subtle variations to one of dramatic contrasts and organized complexity. And like all the other arrows, it points the same direction, forward from the Big Bang, forward toward whatever ultimate fate awaits the cosmos. All these arrows, thermodynamic and electromagnetic, quantum and gravitational, cosmological and microscopic, align perfectly, creating the overwhelming sense of directionality that we call time's passage, the current that carries us inexorably from what was toward what will be. There's a paradox at the heart of physics that has puzzled scientists for more than a century. The fundamental laws governing particles and forces, the equations that describe how matter and energy behave at the deepest level, are almost entirely symmetric with respect to time. Run them forward or backward and they work equally well. Reverse the direction of time in Newton's laws, in Maxwell's equations for electromagnetism, in Schrödinger's equation for quantum mechanics, and you get perfectly valid descriptions of possible physical processes. The laws themselves don't prefer one temporal direction over another. And yet the universe we inhabit is profoundly asymmetric in time. Eggs break but don't spontaneously reassemble. Coffee cools but never spontaneously reheats. We age but never grow younger. The resolution to this paradox lies not in the laws themselves but in the boundary conditions, the specific initial state from which the universe began. Time-symmetric laws produce irreversible behavior when applied to a universe that started in a very special, very low-entropy configuration. The directionality emerges not from the rules of the game but from where the game began. This realization has led physicists to propose what's called the past hypothesis, a foundational assumption that treats the universe's low initial entropy as a fundamental feature requiring no further explanation, or at least accepting it as the key fact upon which everything else depends. According to this view, asking why the Big Bang had low entropy is somewhat like asking why the universe exists at all. It's a boundary condition, a starting point, perhaps the starting point for understanding everything that follows. Some researchers seek deeper explanations, looking to quantum cosmology or theories of eternal inflation that might explain how our particular low-entropy universe came to be. But for practical purposes, for understanding why time flows the way it does, the past hypothesis provides a foundation. Accept that the universe began with remarkably low entropy, and everything else follows. Entropy increases, disorder spreads, time acquires a direction, and all the phenomena we associate with time's passage emerge naturally from that single initial condition. What makes this particularly interesting is how open systems behave. Most systems we encounter in daily life aren't isolated. They exchange energy and matter with their surroundings. And these open systems can decrease their own internal entropy while still obeying the second law of thermodynamics, as long as they export enough entropy to their environment to ensure the total entropy increases. This is how complexity arises. A developing embryo decreases its entropy, taking disordered nutrients and organizing them into structured tissues and organs. But this local decrease in entropy is paid for by much larger increases in entropy elsewhere, in the heat generated by metabolism, in the waste products expelled, in the sun that ultimately powers the entire process. Open systems can develop extraordinary complexity, can create order and structure and organization, not by violating thermodynamics but by cleverly working within it, by channeling flows of energy and matter in ways that build local order at the expense of greater disorder elsewhere. Life itself is the most spectacular example of this process, creating islands of complexity and organization in a universe steadily sliding toward equilibrium. And it's precisely in such low-entropy systems that memory becomes possible. Memory requires a physical record, a pattern impressed upon matter that persists through time. In a high-entropy system near equilibrium, any pattern you try to create would quickly degrade, erased by random thermal fluctuations and the natural tendency toward disorder. But in a low-entropy system far from equilibrium, like a living brain in a living body, patterns can be created and maintained with relative stability. The formation of a memory increases the total entropy of the universe, as all information storage must, but it creates a lasting trace, a record that points backward to past events. This is why memory only forms in systems with relatively low entropy. It's why you can remember yesterday but not tomorrow. The low-entropy state of your brain allows patterns to be written and preserved, creating a record that points backward along time's arrow. In a maximum entropy universe, memory would be impossible. There would be no substrate stable enough to hold patterns, no energy gradients to power the processes of encoding and retrieval. Memory itself is a phenomenon that emerges from time's asymmetry. There's a theorem in statistical mechanics, proven by Henri Poincaré, that states any isolated system will eventually return arbitrarily close to its initial state if you wait long enough. The Poincaré recurrence time for any finite system is finite, though it might be unimaginably large. For something as complex as a room of air, the recurrence time vastly exceeds the current age of the universe by factors so enormous they're hard to comprehend. For the entire observable universe, the recurrence time becomes meaningless in any practical sense. Yes, if the universe were truly isolated and you waited for incomprehensible spans of time, it might eventually fluctuate back to something resembling its current low-entropy state. But this mathematical possibility is utterly irrelevant to human experience, to the flow of time we actually observe, to the asymmetry that defines our existence. We live our lives on timescales of decades, observe processes on timescales of centuries, study cosmic evolution on timescales of billions of years. Poincaré recurrence operates on timescales so vast that they might as well be infinite. Time's arrow is secure for any duration that matters to any observer who could possibly care. Moreover, the universe isn't isolated in the way Poincaré's theorem requires. Space itself is expanding, carrying distant galaxies away from us at ever-increasing speeds. This expansion dilutes energy density, spreads matter and radiation across ever larger volumes, and prevents any possibility of large-scale time reversal. The cosmic expansion is itself an arrow of time, a dynamical feature of the universe that ensures we can never return to previous states. As space expands, it carries the contents of the universe into new configurations, states that have never existed before and will never be repeated. The expansion doesn't just make time reversal unlikely. It makes it geometrically impossible on cosmic scales. The universe's evolution is written not just in the increasing entropy of its contents, but in the increasing size of the stage on which everything unfolds. Meanwhile, in particle physics laboratories around the world, researchers continue to probe the fundamental symmetries of nature. And what they find confirms that time asymmetry isn't just a thermodynamic phenomenon emerging from statistics and large numbers. Certain particle decay experiments, particularly those involving particles called kaons and B mesons, show clear violations of time reversal symmetry. These aren't statistical effects. They're intrinsic properties of the weak nuclear force, one of the four fundamental forces of nature. The asymmetry is tiny, appearing only in specific rare processes, but it's real and measurable. Fire a beam of kaons through a detector and analyze their decay products, and you can distinguish the forward time process from its hypothetical time-reversed counterpart. They don't behave identically. The universe at its most fundamental level, in the realm of quantum fields and fundamental forces, appears to have a preferred temporal direction built into the laws themselves, independent of any thermodynamic considerations. Quantum field theory, the framework that unifies quantum mechanics with special relativity, preserves causality through a fundamental requirement. Fields and their disturbances propagate forward in time only. Information and influence spread outward into the future light cone from any event, but they cannot propagate backward into the past light cone. This structure is built into the mathematical foundations of the theory. Quantum fields obey equations that respect causality, ensuring that causes precede effects, that influences spread forward through time rather than backward. This isn't just a convenient assumption. It's required for the theory to make consistent predictions, to avoid paradoxes, to give results that match experimental observations. The forward propagation of quantum fields provides another layer of temporal asymmetry, another reason why time flows in only one direction at every level of physical description. Even the aging of our bodies, something we experience so personally and directly, aligns perfectly with thermodynamic time. Biological systems maintain their organization by constantly consuming energy and expelling entropy. But this process isn't perfectly efficient, and over time, damage accumulates. Cells make copying errors when replicating DNA. Proteins misfold and aggregate. Metabolic byproducts cause oxidative damage. The body's repair mechanisms, sophisticated as they are, can't keep up forever. Aging is fundamentally a thermodynamic process, a gradual increase in disorder and damage within biological systems despite their best efforts to maintain organization. We age forward through time because entropy increases, because repair is never perfect, because the thermodynamic arrow points inexorably from youth to age, from vigor to frailty, from low entropy to high. Our bodies are clocks, marking time's passage through the accumulation of molecular disorder. And surrounding us in all directions, filling the universe with faint microwave radiation, is the cosmic microwave background, the afterglow of the Big Bang itself. This radiation was released when the universe was about 380,000 years old, when it had cooled enough for atoms to form and light to travel freely through space. That radiation has been cooling ever since, stretched by cosmic expansion from visible light into microwaves, from temperatures of thousands of degrees to just under 3 degrees above absolute zero. This cooling is irreversible. The cosmic microwave background is a snapshot of a hotter, denser, lower entropy past, and its existence in our present, now cooled and diluted, is direct evidence of time's arrow operating on cosmic scales. Every measurement of this radiation confirms what thermodynamics predicts. The universe was hotter in the past, is cooler in the present, and will be cooler still in the future. The cooling is monotonic, always in the same direction, a cosmic scale thermometer measuring the universe's inexorable progression from the intense heat of its beginning toward the cold emptiness of its distant future. Time moves forward, and the cooling of the cosmos is both evidence and consequence of that fundamental directionality. The universe is getting larger. Not just in the sense that galaxies are moving apart, though they are, but in a more fundamental way. Space itself is expanding, stretching the very fabric of reality, increasing what cosmologists call the scale factor, a mathematical measure of the universe's size relative to some reference point. And this expansion is directional. The scale factor increases with time. It doesn't oscillate, doesn't reverse, doesn't fluctuate randomly. It grows steadily, monotonically, marking time's passage in the most cosmic way imaginable. When we say time moves forward, we can point to this increasing scale factor as a physical manifestation of that directionality. The universe was smaller in the past, is larger now, and will be larger still in the future. This alignment between time and the universe's expansion isn't a coincidence. They're both expressions of the same underlying evolution, the same journey from the dense, hot conditions of the Big Bang toward the dilute, cool conditions of the distant future. Time and space are expanding together, and that expansion gives time an arrow as fundamental as any arrow thermodynamics provides. Black holes complicate and deepen this picture in fascinating ways. When matter falls into a black hole, crossing that point of no return we call the event horizon, something profound happens to information. From the outside perspective, the information about the specific quantum state of that matter, all the details that distinguished one arrangement of particles from another, becomes permanently inaccessible. The black hole retains only a few properties like mass, charge, and angular momentum. Everything else, all the complexity and specificity of what fell in, is lost to the outside universe. This represents a profound form of irreversibility. You cannot recover the initial state from the final state because the final state doesn't contain enough information. The black hole has erased the details, hidden them behind a horizon from which no signal can escape. Whether information is truly destroyed or merely hidden in ways we don't yet understand remains one of physics' deepest puzzles. But either way, black holes demonstrate irreversibility at its most extreme, regions of spacetime where the past becomes permanently disconnected from the future, where time's arrow is enforced by the geometry of space itself. The structure of spacetime itself restricts how influence and causality can flow. At any event, any point in spacetime, you can define what's called the light cone, the boundary formed by all possible paths that light could take from that event. The future light cone encompasses all events that could possibly be affected by what happens here and now. The past light cone encompasses all events that could have influenced what happens here and now. And these cones only open toward the future and past respectively. They don't mix. Causal influence flows exclusively into the future light cone. You can affect the future, but you cannot affect the past. Information and energy propagate forward along and within the future light cone, but they cannot loop back to earlier times. This structure is built into the geometry of spacetime as described by relativity. It provides a geometric foundation for causality, a mathematical guarantee that causes precede effects, that influence flows forward through time rather than backward. The light cone structure is yet another manifestation of time's one-way nature, encoded in the very shape of spacetime itself. In the quantum realm, where particles exist in superpositions of states until measured, the progression of time manifests in subtle but important ways. Even if you don't fully accept the idea of wave function collapse as a physical process, quantum measurements still progress forward in time. Decoherence, the process by which quantum superpositions interact with their environment and lose their quantum properties, happens in one direction. A quantum system interacting with its surroundings evolves from a pure superposition toward a mixed state that behaves classically. This process is irreversible. You can't simply undo the environmental interactions and restore the original quantum coherence. The quantum to classical transition has a directionality, pointing from the microscopic quantum realm toward the macroscopic classical world we observe. Even in the strange domain of quantum mechanics, where so many of our classical intuitions fail, time maintains its forward flow. There's a limit to how much you can order a physical system, how low you can push its entropy, and that limit is expressed in the third law of thermodynamics. Absolute zero, the temperature at which all thermal motion would cease, cannot be reached by any finite series of processes. You can get arbitrarily close, cooling systems to millionths of a degree above absolute zero, but you can never quite reach zero itself. This impossibility reinforces irreversibility in a subtle but profound way. It means there's always some thermal motion, always some residual disorder, always some minimum entropy that cannot be eliminated. Perfect order is unattainable. The universe maintains a floor beneath which entropy cannot fall, ensuring that the thermodynamic arrow of time remains meaningful even in the coldest systems we can create. The unattainability of absolute zero is another way nature prevents time reversal, another barrier against returning to perfect low-entropy states. Ludwig Boltzmann provided a mathematical formulation of entropy increase through what's now called the H-theorem. He defined a quantity called H, related to the entropy of a gas, and showed that under certain assumptions about molecular collisions, H must decrease monotonically, which corresponds to entropy increasing monotonically. This was one of the first mathematical demonstrations that irreversibility could emerge from reversible microscopic laws through statistical behavior. The H-theorem captures in equations what we've been describing in words. When you have large numbers of particles following simple rules, their collective behavior favors certain directions of evolution. The theorem has limitations and sparked debates about its assumptions, but it represents a crucial step in understanding how time asymmetry emerges from symmetric underlying laws. It shows that entropy increase isn't just an empirical observation but a mathematical consequence of statistical mechanics, derivable from first principles given appropriate initial conditions. And yet, as we've noted, entropy can decrease locally. A refrigerator cools its interior. A plant builds complex molecules from simple ingredients. A crystal forms from solution, creating exquisite order where none existed before. These local entropy decreases are real and important. They're how complexity arises, how structure forms, how interesting things happen in a universe moving toward disorder. But every local entropy decrease is offset by larger global increases. The refrigerator dumps heat into the room. The plant absorbs solar energy that originated in fusion reactions in the sun, processes that vastly increase entropy. The crystal forms because the solution releases heat, spreading energy and increasing entropy in the surrounding environment. When you properly account for all the entropy changes, including those in the environment and in the energy sources powering the process, the total always increases. This is how the second law accommodates the existence of complexity and order. It doesn't forbid local decreases. It simply requires that they're paid for with even larger increases elsewhere. The universe can create islands of order in a sea of growing disorder, and in those islands, remarkable things can happen. Quantum decoherence, the process by which quantum systems lose their coherence through interaction with the environment, is fundamentally irreversible. When a quantum superposition decoheres, when the delicate quantum correlations between different possible states are destroyed by environmental interactions, the system transitions from quantum to classical behavior. The many interfering possibilities collapse into a statistical mixture where quantum interference effects vanish. And this process only goes one direction. You can decohere a quantum state, but you can't easily recohere it, can't restore the intricate quantum correlations that were destroyed. In practice, decoherence is effectively irreversible for any macroscopic system. This is why we don't see quantum superpositions in everyday life, why cats are either alive or dead rather than both simultaneously. Decoherence suppresses quantum behavior irreversibly, creating another arrow of time, another process that distinguishes past from future at the quantum level. There are limits to how much information you can pack into a given volume of space, and these limits are intimately connected to entropy. The Bekenstein bound states that the maximum entropy that can be contained in a given region is proportional to the area of the region's boundary, not its volume. This surprising result connects information theory, thermodynamics, and quantum gravity in deep ways. Black holes saturate this bound, containing the maximum possible entropy for their size. What this means for time's arrow is that there are fundamental limits to how ordered, how low in entropy any region of space can be. You cannot compress information infinitely, cannot reduce entropy arbitrarily in a finite volume. These bounds ensure that entropy has room to grow, that the universe's journey from low to high entropy can continue for vast spans of time before approaching any fundamental limits. The entropy bounds are another way physics ensures that time keeps its direction, that there's always more disorder possible in the future than existed in the past. Finally, consider what happens in chaotic systems, those exquisitely sensitive configurations where tiny differences in initial conditions lead to wildly different outcomes. Chaos amplifies uncertainty forward in time. If you know a system state with imperfect precision, which is always the case in practice, that small uncertainty grows exponentially as the system evolves. Weather is the classic example. Small measurement errors or tiny unmodeled effects become magnified until prediction becomes impossible beyond a certain horizon. Importantly, this amplification is asymmetric in time. Uncertainty grows rapidly when you try to predict the future, but it can be reduced when you retrodict the past, when you work backward from present observations to infer earlier states. Chaotic systems remember their past more faithfully than they reveal their future. This provides yet another arrow, another asymmetry distinguishing forward from backward. The future is fundamentally more uncertain than the past, not just because we lack information, but because the dynamical laws themselves amplify uncertainty in the forward direction. Time's arrow is written into the mathematics of chaos, ensuring that even if we knew all the laws and had perfect computational power, the future would remain more mysterious than the past, more open, more unknowable. The universe unfolds into possibilities that multiply and diverge, and we ride that wave of increasing uncertainty from the determined past toward the open future. There's a mathematical framework called Markov processes that describes how systems evolve when the future depends only on the present, not on the detailed history of how the present came to be. A particle undergoing random motion, a stock price fluctuating, a gene spreading through a population, these can often be modeled as Markov processes. And these processes have a characteristic feature. They evolve probability distributions forward in time. Given the current state, you can calculate the probability distribution of future states. The mathematics naturally points forward, taking present configurations and projecting them into arrays of possible futures. While you can sometimes infer something about the past from present observations, The Markov framework is fundamentally forward-looking. It's built around the idea of time flowing from now toward what comes next. This mathematical structure mirrors the physical reality of time's arrow. The equations we use to describe evolving systems naturally incorporate directionality, treating the future as something to be calculated from the present rather than treating past and future symmetrically. Evolution, the grand biological process that shaped all life on Earth, demonstrates time's arrow with particular clarity. Evolutionary history branches forward. Species diverge, populations split, new forms emerge from ancestral ones. The tree of life grows from roots toward branches, from simple beginnings toward increasing diversity and complexity. You never see the reverse. Separate species don't spontaneously merge into a single ancestor. Diversity doesn't collapse back into simplicity. The branching pattern of evolution is irreversible, a biological manifestation of thermodynamic and historical directionality. Each generation inherits genetic information from the previous generation, occasionally modified by mutation and recombined through sexual reproduction. The flow of genetic information is forward, from ancestors to descendants, creating a living record of time's passage written in DNA sequences across millions of species. Even in the strange realm of particle physics, where particles can oscillate between different states, where matter can transform into antimatter and back again, causality remains respected. Certain neutral particles, like neutrinos and some mesons, can oscillate, changing their identity as they propagate through space. A particle created in one state might be detected in a different state sometime later. These oscillations are real quantum mechanical phenomena, but they don't violate causality. The oscillations happen as the particle moves forward through time, from creation event to detection event. The mathematics describing these oscillations is built on quantum field theory, which, as we've discussed, preserves forward causality. The particle's wave function evolves forward, and the oscillations are part of that forward evolution. Time's arrow is maintained even when particles are doing seemingly paradoxical things like changing their fundamental identity as they travel. When physicists draw space-time diagrams, visual representations of how objects move through space and time, they follow certain conventions that reflect time's directionality. Time typically points upward on these diagrams. World lines, the paths objects trace through space-time, extend from past to future, from bottom to top. And when you extend these diagrams to consider the ultimate fate of the universe, you find future infinities, asymptotic regions where time continues indefinitely forward. But there are no past-directed paths that loop back to earlier times. The diagrams themselves enforce causality. Light cones open toward the future, not the past. Time-like paths that represent possible trajectories for massive objects always move forward in time. The geometry of space-time as captured in these diagrams is fundamentally asymmetric. Past and future play different roles. The diagrams are maps of possibility, and they show clearly that backward time travel, motion along paths that curve back to earlier times, is not part of the accessible landscape for any ordinary object or signal. Information theory reveals another profound connection to time's arrow through a principle known as Landorus principle. It states that erasing information, resetting a bit from 1 to 0 or eliminating a record, necessarily dissipates heat and increases entropy. Information has a physical cost. You cannot delete what was written without leaving a thermodynamic trace. This means that computation, memory management, any process involving information manipulation, is fundamentally irreversible at the thermodynamic level. Even if your logic gates and memory cells were perfectly reversible in principle, the act of erasing information to reuse memory or reset a computer requires energy dissipation. This links information theory directly to thermodynamics, showing that information is not abstract but physical, that manipulating it has energetic consequences, and that those consequences respect time's arrow. Every erased hard drive, every cleared memory register, every forgotten thought leaves its mark as heat dissipated into the environment, entropy spread into the world. Some approaches to quantum gravity, attempts to unify quantum mechanics with general relativity, suggest that time itself might be emergent rather than fundamental. In these models, space-time and temporal flow arise from more basic quantum information or entanglement structures. Time might not be a primary feature of reality but something that emerges at larger scales from timeless quantum processes. And yet, even in these radical frameworks, when time emerges, it emerges with a direction. The models that have been explored still produce a thermodynamic arrow, still generate a distinction between past and future at the scales where time becomes meaningful. Whether time is fundamental or emergent, whether it's written into the deepest laws or arises from quantum information, the directionality persists. This suggests that time's arrow is remarkably robust, not dependent on any particular interpretation of time's nature, but a feature that emerges from physical law and cosmic history regardless of the ultimate foundation. Acceleration itself, the change in velocity, produces asymmetric effects when analyzed carefully. This is captured by something called the Unruh effect. An observer undergoing constant acceleration through empty space will perceive a thermal bath of particles, a kind of radiation that depends on the acceleration. But this effect is asymmetric. Accelerating forward through space-time is different from accelerating backward. The thermal radiation an accelerated observer experiences depends on their trajectory through space-time, and that trajectory has a direction. Similarly, Hawking radiation from black holes, another thermal effect related to acceleration and gravity, represents an irreversible process. Black holes radiate, slowly losing mass over enormous timescales, and this radiation is directional, flowing outward from the horizon into the external universe. These connections between acceleration, thermality, and asymmetry reveal deep relationships between motion, gravity, and time's arrow. Look up at the stars and you're seeing the products of nuclear fusion, the process that powers stellar interiors. Hydrogen fuses into helium, helium into carbon and oxygen, and in the most massive stars, fusion continues through silicon and sulfur toward iron. This sequence is directional. Stars build heavier elements from lighter ones, never the reverse. Iron represents a terminus because fusing iron requires energy input rather than releasing energy. The fusion chain in stars moves forward through the periodic table, creating the chemical diversity of the universe element by element. And this process is irreversible. Once fusion has occurred, once light nuclei have combined into heavier ones and released their binding energy, that energy spreads outward as light and heat, increasing entropy, never spontaneously gathering back together to reverse the fusion. The nucleosynthesis in stars is cosmic alchemy running in only one direction, from simple to complex, from light to heavy, following time's arrow from the Big Bang's hydrogen and helium toward the rich chemical tapestry of the modern universe. Gravitational instability drives another forward process. In the early universe, matter was distributed almost uniformly, with only tiny density fluctuations. But gravity is unstable. Regions slightly denser than average attract more matter, becoming denser still. This runaway process drives gravitational collapse, forming dark matter halos, galaxies, star clusters, and ultimately stars and planets. Structure grows through gravitational instability, moving from smooth to clumpy, from uniform to hierarchical. And this process is directional. You don't see large-scale structure spontaneously dissolving back into smooth uniformity. The cosmos moves from simplicity toward complexity through gravitational collapse, and that collapse has a temporal direction. It moves forward from the smooth early universe toward the richly structured universe we inhabit. Gravity, despite its long-range and attractive nature, produces asymmetry in time through instability and collapse. And finally, there's a profound anthropic consideration. For observers like us to exist, to think about time and entropy and causality, the universe must have begun in a low-entropy state. Conscious beings are complex structures, far from thermodynamic equilibrium, requiring specific conditions and histories to form. We are products of stellar nucleosynthesis, of planet formation, of chemical evolution, of biological evolution, all processes that depend on the universe having substantial entropy gradients, energy flows, disequilibrium conditions. In a high-entropy universe near thermal equilibrium, none of these processes could occur. Observers require low-entropy beginnings because only in such conditions can the complex, ordered structures necessary for life and consciousness emerge. Our very existence as thinking beings capable of wondering about time's direction is evidence that the universe began in a special state. The fact that we're here, contemplating these questions, tells us something profound about cosmic history. It tells us that time has been flowing forward from a low entropy beginning for billions of years, creating the conditions, the structures, the chemical elements, and the energy flows necessary for complexity and consciousness to arise. We are, in a sense, witnesses to time's arrow, but more than that, we are products of it, beings whose existence depends utterly on the universe's journey from order to disorder, from simple to complex, from past to future. Entropy increase doesn't just correlate with time's direction. In a very real sense, it creates that direction, defines what we mean when we say forward and backward. Without entropy growth, without the thermodynamic arrow pointing from order toward disorder, time would lose its asymmetry. The universe would be fundamentally different, perhaps static, perhaps fluctuating randomly without any meaningful distinction between past and future. But in our universe, entropy provides a universal compass, a direction that applies everywhere and always. Whether you're on Earth or in a distant galaxy, whether you're observing chemical reactions or cosmic evolution, entropy increases. This universality is remarkable. Despite the vast diversity of physical processes, despite the enormous range of scales from atoms to galaxy clusters, despite the complexity of interactions and forces, everything follows the same thermodynamic direction. Entropy increase creates a universal arrow that threads through all of physics, connecting the microscopic to the macroscopic, the local to the cosmic, giving time its essential character as something that flows rather than merely exists. Heat flow provides one of the most familiar examples of this directionality. Place a hot object in contact with a cold object and heat flows from hot to cold. Always. Without exception. The temperatures equalize, the hot object cooling and the cold object warming until they reach the same temperature. This happens spontaneously, inevitably, requiring no external intervention. But the reverse never occurs. Two objects at the same temperature never spontaneously develop a temperature difference, with one becoming hotter while the other becomes cooler. Heat doesn't flow from cold to hot without work being done, without energy being input from outside. This asymmetry in heat flow is so fundamental, so utterly reliable, that entire branches of engineering are built upon it. Engines work because heat flows naturally from hot to cold, and we can extract useful work from that flow. Refrigerators work by forcing heat to flow from cold to hot, but they require energy input to accomplish this unnatural direction. The spontaneous flow of heat from hot to cold is time's arrow made tangible, thermal energy spreading from concentrated form to dispersed form, never reversing without external intervention. Diffusion operates on similar principles but applies to matter rather than heat. Drop a colored dye into water and watch it spread. The concentrated drop disperses, molecules moving from regions of high concentration to regions of low concentration, spreading outward until the color is uniform throughout the water. This is diffusion, and it's entirely directional. You never see the reverse. You never see uniformly colored water spontaneously gathering all its dye molecules back into a concentrated drop, leaving clear water everywhere else. The molecules spread from concentration to uniformity because there are vastly more configurations corresponding to uniform distribution than to concentrated distribution. Diffusion is entropy increase made visible, disorder spreading through space as molecular motion carries substances from where they're concentrated to where they're sparse. And like all entropy-driven processes, it runs in only one direction, following time's arrow from organized to dispersed, from structured to uniform. The expansion of the cosmos itself demonstrates time's directionality on the largest possible scale. Space is stretching, carrying galaxies away from each other, and this expansion dilutes matter density over time. The universe was denser in the past, is less dense now, will be less dense still in the future. This trend is monotonic, always moving in the same direction. As expansion continues, the average distance between galaxies grows, the average density of matter decreases, and the universe becomes increasingly empty. This cosmic dilution is irreversible. Expansion doesn't reverse, doesn't alternate with contraction in our universe. It continues steadily, driven by the universe's energy content and geometry, carrying everything toward a future of increasing emptiness and isolation. The dilution of matter through cosmic expansion is another manifestation of time's arrow, written not in thermodynamics but in the dynamics of space-time itself. And as space expands, it stretches the radiation that fills it, including the cosmic microwave background we discussed earlier. This stretching shifts the radiation toward longer wavelengths, toward lower energies, cooling it irreversibly. The cosmic microwave background was hot when it was released, thousands of degrees, appearing as visible light. But billions of years of expansion have stretched those waves into microwaves, cooled that radiation to just under 3 degrees above absolute zero. And the cooling continues. As the universe expands further, the background radiation will cool further, shifting from microwaves toward radio waves, from 3 degrees toward 2 degrees toward 1 degree, asymptotically approaching but never reaching absolute zero. This cooling is completely irreversible. The stretched photons cannot unstretch themselves, cannot spontaneously gain energy and shift back toward shorter wavelengths. The cooling of background radiation through cosmic expansion is a thermodynamic process operating on the scale of the entire observable universe, marking time's passage in the gradual chilling of the cosmos. Quantum decoherence, that process by which quantum superpositions lose their coherence through environmental interaction, produces behavior that mimics classical irreversibility even though the underlying quantum mechanics remains time-symmetric. When a quantum system decoheres, it transitions from a state of quantum coherence where different possibilities interfere with each other to a classical mixture where interference effects vanish. This transition happens rapidly and comprehensively for macroscopic objects. A large object like a dust grain or a biological cell decoheres so quickly that maintaining quantum coherence is essentially impossible. And once decoherence has occurred, restoring coherence requires isolating the system from its environment and carefully reversing all the environmental interactions, a task that becomes exponentially harder as system size increases. For practical purposes, decoherence is irreversible. It provides a bridge between quantum mechanics and classical physics, explaining why we don't observe macroscopic superpositions, and it does so through a process that respects time's arrow. Quantum systems evolve from coherent to decoherent, from quantum to classical, in a directional manner that aligns perfectly with thermodynamic irreversibility. We've mentioned CP violation before, but its significance deserves emphasis. In certain particle interactions, particularly those involving the weak nuclear force, there's a fundamental asymmetry between matter and antimatter processes. This CP violation is not a statistical effect or an emergent phenomenon. It's built into the basic laws of particle physics, encoded in the properties of the weak force and the masses and mixing of quarks. When physicists measure these processes precisely, they find small but definite differences between processes and their CP conjugated counterparts. And through a deep theorem in quantum field theory called Kaplan symmetry, which states that the combined operations of charge conjugation, parity reversal, and time reversal must be a symmetry of any consistent quantum field theory, CP violation implies time reversal violation. The fundamental laws at the particle level are not time-symmetric. They have a preferred direction, a built-in arrow that operates independently of thermodynamics or cosmology. This microscopic arrow might seem disconnected from the macroscopic arrow we experience, but it hints that time's asymmetry is woven deeply into the fabric of physical law at multiple levels. Event horizons, those boundaries surrounding black holes where escape becomes impossible, enforce time's directionality in the most absolute way imaginable. Once something crosses an event horizon, every possible future path leads inward toward the singularity. There is no trajectory, no amount of acceleration, no clever maneuver that can reverse this fate. The geometry of spacetime inside the horizon is such that the singularity lies in every path's future, just as surely as tomorrow lies in your future outside a black hole. Attempting to escape would be like trying to prevent tomorrow from arriving. It's not merely difficult or requiring vast energy. It's geometrically impossible. The event horizon blocks any past-directed escape. It's a one-way membrane in spacetime, permeable only in the forward temporal direction. Black holes are regions where time's arrow is enforced by causal structure itself, where attempting to reverse time's flow would require violating the most basic rules about how space-time fits together. Relativity teaches us that time is flexible, that clocks can tick at different rates depending on motion and gravity. Travel at high speed relative to another observer and your clock runs slower compared to theirs. Descend into a strong gravitational field and your clock slows relative to clocks in weaker gravity. These effects are real and measurable. GPS satellites must account for time dilation to maintain accurate positioning. Particles moving near light speed in accelerators live longer than identical particles at rest, their internal clocks slowed by their motion. But notice what doesn't happen. Time dilation alters the rate at which time passes, but never its direction. A clock in a gravitational field ticks slower but still ticks forward. A clock on a fast-moving spacecraft runs slow compared to Earth clocks but still marks the progression from past to future. You can stretch time, compress it, make it pass at different rates for different observers, but you cannot reverse it. The flexibility of time in relativity is a flexibility of rate, not direction. All observers, regardless of their motion or gravitational environment, agree on the direction of time even when they disagree on its rate. And underlying all of this, providing the statistical foundation for time's arrow, is probability itself. The laws of probability suppress macroscopic reversals with such overwhelming force that they effectively become impossible. Yes, the fundamental laws of physics are mostly time-symmetric. Yes, there's no absolute prohibition on a broken egg reassembling itself or spilled water flowing back into a glass. But the number of ways these reversals could occur is so vanishingly small compared to the number of ways the forward process can continue that probability makes reversal effectively impossible. It's the same reason you don't worry about all the air molecules in a room spontaneously gathering in one corner, leaving you to suffocate in vacuum everywhere else. The probability isn't exactly zero, but it's so small that it might as well be. Macroscopic reversals require such precise coordination of astronomical numbers of particles that the probability becomes meaningless in any practical sense. Probability doesn't just favor forward evolution. It mandates it with a certainty that approaches absolute for any system of appreciable size. The universe moves forward not because it's forced to by some external law, but because forward is where probability overwhelmingly points, where the vast majority of possible futures lie, where the natural flow of increasing disorder inevitably leads. Time moves forward because forward is almost the only direction there is. Your body is a chronicle of time's passage, written in molecules and cells. Every breath you take, every heartbeat, every thought, every movement generates wear at the microscopic level. DNA accumulates mutations as copying errors slip through repair mechanisms. Proteins fold incorrectly and aggregate into clumps that interfere with cellular function. Free radicals damage membranes and molecular machinery. Telomeres, the protective caps on chromosomes, shorten with each cell division until cells can no longer divide. These biological processes accumulate damage forward through time. You don't spontaneously grow younger. Scars don't vanish. Wrinkles don't smooth themselves. The damage is cumulative, progressive, directional. Your body maintains itself remarkably well, deploying sophisticated repair mechanisms, replacing damaged components, fighting entropy at every level. But the fight is ultimately a delaying action, not a victory. Damage accumulates faster than it can be fully repaired, and this accumulation defines aging, defines the biological arrow of time that carries every living thing from birth through maturity toward eventual death. We are temporal beings not just because we exist in time, but because time is written into our biology, inscribed in the gradual accumulation of molecular disorder that accompanies every moment of life. Yet entropy doesn't increase with perfect monotonicity at small scales. There's a beautiful set of mathematical results called fluctuation theorems that quantify how often and by how much entropy can briefly decrease in small systems observed for short times. These theorems describe the probability of observing entropy-decreasing fluctuations, and they show that such fluctuations become exponentially less likely as the size of the decrease grows or the observation time lengthens. For a tiny system observed briefly, you might occasionally see entropy drop slightly. But for larger systems or longer times, these violations become vanishingly rare. The fluctuation theorems provide precise mathematical descriptions of the relationship between forward and backward processes, showing that time-reverse paths, while not impossible, are exponentially suppressed by probability. These theorems don't overturn the second law. They refine it, showing exactly how rare exceptions can be while confirming that the overwhelming trend is always toward entropy increase. They reveal that nature permits small, temporary violations of the thermodynamic arrow while ensuring that any substantial or lasting reversal remains impossible. When you do work on a system, forcing it to change in some way, the work required depends on whether you're driving the system forward or backward through its state space. This is captured in what's called non-equilibrium thermodynamics. In general, forward processes that increase entropy dissipate energy efficiently, losing it as heat to the environment. But trying to reverse these processes, to decrease entropy and restore earlier states, requires much more work. The dissipation favors the forward direction. It's easier to scramble an egg than to unscramble it, easier to mix cream into coffee than to separate it back out, easier to heat a room than to cool it. This asymmetry in work requirements is another manifestation of time's arrow. Nature resists backward processes, making them thermodynamically expensive, while allowing forward processes to proceed with relative ease. The dissipation of energy in irreversible processes is not just waste. It's the signature of time's direction, the thermodynamic cost of moving forward through state space along paths that increase entropy. The statistical mechanics underlying all of this tells us something profound about the relative frequency of different temporal paths. For any macroscopic system, the number of microscopic configurations corresponding to higher entropy vastly outnumbers those corresponding to lower entropy. This means that time-reverse paths, which would require moving from higher entropy states to lower entropy states, are exponentially rarer than forward paths. The ratio of forward to backward paths grows exponentially with system size and entropy difference. For a glass of water, the number of forward evolutionary paths outnumbers backward paths by factors so enormous they defy comprehension. For the universe as a whole, the disparity is even more extreme. Time-reverse paths exist in the space of logical possibilities, but they occupy such a vanishingly small fraction of that space that encountering one by chance would require waiting far longer than the universe has existed or will exist. The rarity of time-reverse paths is the mathematical foundation of time's arrow, the reason probability so strongly favors forward evolution. Black holes, despite being regions where matter and energy disappear from the observable universe, ultimately contribute to entropy increase through a remarkable process discovered by Stephen Hawking. Black holes aren't perfectly black. They emit radiation, a quantum mechanical effect arising from particle creation near the event horizon. This Hawking radiation is thermal, characterized by a temperature inversely proportional to the black hole's mass. As a black hole radiates, it loses mass, shrinking slowly, and as it shrinks, its temperature rises and it radiates faster. Eventually, over timescales incomprehensibly longer than the current age of the universe for stellar mass black holes, a black hole will evaporate completely. And crucially, this evaporation increases the total entropy of the universe. The radiation carries away entropy, and when you properly account for both the black hole's entropy and the entropy of the radiation it produces, the total entropy increases. Black hole evaporation is another irreversible process, another manifestation of time's arrow operating at the intersection of quantum mechanics, general relativity, and thermodynamics. The universe's expansion is not just continuing but accelerating, driven by what cosmologists call dark energy, a mysterious component that causes space itself to expand at an ever-increasing rate. This accelerating expansion has profound implications for time's direction. It prevents any future recollapse. Earlier cosmological models sometimes featured oscillating universes that would expand, reach a maximum size, then contract back to a big crunch, potentially bouncing into a new expansion phase. But the accelerating expansion rules out such scenarios for our universe. We're not heading toward a future contraction. We're heading toward ever greater expansion, ever-increasing distance between galaxy clusters, ever greater dilution of matter and energy. The acceleration ensures that the universe's expansion is irreversible, that the cosmic arrow of time points definitively forward toward a cold, dark, empty future rather than cycling back toward another dense, hot state. The discovery of accelerating expansion removed any possibility of temporal cyclicity, confirming that the universe has a definite trajectory from its Big Bang beginning toward its asymptotic future. When we observe the large-scale structure of the universe, the cosmic web of galaxies and galaxy clusters, we're seeing the result of irreversible assembly processes. Galaxies don't spring into existence fully formed. They assemble hierarchically from smaller structures over billions of years. Small dark matter halos form first, drawing in gas that cools and forms stars. These small galaxies merge to form larger galaxies. Clusters assemble from multiple galaxies drawn together by gravity. The structure we observe today is the accumulated result of countless mergers, collisions, and gravitational interactions. And this assembly is irreversible. Galaxies don't spontaneously disassemble into dispersed gas and dark matter. Clusters don't dissolve back into isolated galaxies. Once structure has formed through gravitational collapse and hierarchical assembly, it remains, continuing to evolve but never reversing its fundamental organization. The assembly of cosmic structure is a one-way process, moving from smooth to clumpy, from simple to complex, from small structures to large structures, following time's arrow from the universe's uniform beginning toward its structured present and future. In quantum field theory, causality is maintained through a specific mathematical requirement. When you calculate how a field responds to a disturbance, the response is retarded, meaning it occurs after the disturbance, not before. This is built into the mathematical structure through what are called retarded Green's functions, which describe how disturbances propagate forward through space-time. The theory could be formulated with advanced Green's functions, which would describe responses that occur before their causes, but these don't match physical reality. Nature uses retarded responses. Effects follow causes. Influences propagate forward in time. This mathematical structure in field theory enforces causality at the most fundamental level, ensuring that the quantum fields underlying all matter and forces respect time's direction. The retarded nature of field responses is another way time asymmetry appears in fundamental physics, another reason why forward and backward are not equivalent in our universe. The observation of direct time reversal violation in particle physics represents one of the most profound experimental confirmations of fundamental time asymmetry. In experiments studying the decay of particles called kaons, Physicists have directly measured that the probability of a certain decay process differs from the probability of the time-reversed process. This isn't inferred from CP violation through theoretical arguments. It's directly measured time reversal violation, observation of processes that behave differently when time's direction is reversed. The effect is small, requiring extraordinary experimental precision to detect, but it's real and reproducible. These experiments prove that at the level of fundamental particle interactions, time has a preferred direction built into the laws of physics themselves. This microscopic arrow doesn't explain why coffee cools or why we age, but it reveals that time asymmetry is woven into nature at the deepest level we can experimentally probe. The weak nuclear force, one of nature's 4 fundamental forces, responsible for radioactive decay and crucial for the nuclear reactions that power the sun, exhibits a peculiar property. It violates a symmetry called parity, treating left and right differently, and it violates charge conjugation, treating particles and antiparticles differently. These violations are manifestations of symmetry breaking, ways in which the weak interaction fails to respect symmetries that other forces obey. And through these broken symmetries, the weak force introduces biases, preferred directions, asymmetries that distinguish one type of process from another. These biases are related to the time reversal violation we just discussed and to the overall CP violation observed in weak interactions. The breaking of these symmetries means that the weak force doesn't treat all directions in abstract symmetry space equivalently. It has preferences, biases, built-in asymmetries. And these asymmetries, while operating at microscopic scales in particle decays, are fundamental features of the laws of nature, evidence that perfect symmetry is not required or even present in the actual physics governing our universe. The weak interaction breaks symmetries, and in doing so, it contributes to the overall pattern of temporal asymmetry that defines how nature operates, adding another layer to the multiple arrows that all point from past toward future. Certain physical systems have a remarkable tendency to organize themselves into what scientists call critical states, balanced on the edge between order and chaos. Sand piles provide a classic example. As you slowly add grains to a pile, the slope gradually increases until it reaches a critical angle. At this point, adding more grains triggers avalanches of all sizes, from tiny shifts of a few grains to massive collapses reshaping the entire pile. The system self-organizes toward this critical state without external direction, guided only by local interactions between grains and the influence of gravity. And this progression toward criticality is directional, moving forward through time as the system explores its state space and settles into characteristic patterns of behavior. Self-organized criticality appears in earthquakes, forest fires, neural networks, financial markets, and countless other systems where components interact locally to produce complex global behavior. These systems don't self-organize backward. They don't spontaneously move away from critical states toward simpler, less organized configurations. They progress forward, developing complexity and structure, finding critical points where they balance between competing tendencies. Self-organization is another manifestation of time's arrow, another way systems evolve directionally even without external guidance. Fractal patterns, those infinitely detailed structures that look similar at every scale of magnification, often grow through irreversible processes. Snowflakes crystallize, adding molecules at their edges in patterns determined by temperature and humidity, creating intricate six-fold symmetric structures that never repeat in exact detail. Coral reefs grow through countless individual polyps depositing calcium carbonate, building elaborate branching structures over decades and centuries. River networks carved their fractal patterns into landscapes through erosion that removes material, transporting it downstream, shaping the land in ways that reflect both randomness and physical law. Lightning branches as it seeks the path of least resistance from cloud to ground, creating fractal trees of electrical discharge. In every case, the fractal growth expands irreversibly. Snowflakes don't melt in reverse, depositing molecules in the exact inverse sequence of their formation. Coral doesn't grow backward. Rivers don't fill in their channels and smooth the landscape. Lightning doesn't retrace its path backward from ground to cloud. Fractal growth, like all physical processes, follows time's arrow, building complexity forward, never reversing its elaborate patterns. Learning, whether in biological brains or artificial neural networks, is fundamentally a forward process of accumulating information. When you learn something new, connections in your brain strengthen or weaken, new synapses form, patterns of neural activity shift to encode the new information. Each experience, each lesson, each moment of practice leaves its mark, gradually building knowledge and skill. This accumulation moves forward through time. You don't spontaneously unlearn things, don't have synapses disconnect in the exact reverse order they formed, don't lose knowledge in the precise inverse sequence you gained it. Learning systems, whether biological or artificial, accumulate information forward, building on past experience to shape future responses. The learning process increases the system's information content, reducing its uncertainty about the world, and this reduction happens directionally. An untrained neural network starts with random weights. Through training, it develops structured connections that encode useful patterns. This progression from random to structured, from ignorant to knowledgeable, is irreversible. Learning systems follow time's arrow, accumulating information as they move from past toward future. Astronomers observing distant objects watch them fade over time in predictable ways. Supernovae, the violent explosions of dying stars, brighten rapidly, then fade over weeks and months following characteristic light curves. Variable stars pulse with regular periods, their brightness rising and falling in patterns that persist over years. Active galactic nuclei flicker and flare as matter falls into supermassive black holes. In every case, the evolution of brightness over time is predictable, following physical laws that govern energy release and propagation. These astronomical light curves fade in specific ways because they reflect irreversible processes. The energy from a supernova disperses outward, spreading into space, never spontaneously reconcentrating to make the supernova brighten again. Variable stars pulse forward through their cycles, never reversing their pulsation. The light curves astronomers measure are temporal signatures of physical processes, and they all follow time's arrow, evolving from bright to dim, from energetic to dispersed, from initial explosion or flare toward eventual quietude. The rocks beneath our feet preserve detailed records of the past through their isotopic composition. Radioactive isotopes decay at known rates, transforming into different elements as time passes. By measuring the relative abundance of parent and daughter isotopes in minerals, geologists can determine when those minerals formed, creating a chronological history written in atomic ratios. These isotopic records preserve formation history in a directional way. The parent isotopes decrease while daughter isotopes increase, and this progression is monotonic, always moving in the same direction as time advances. You can read the age of a rock by reading its isotopic composition, and that age always increases as you examine successively deeper or older layers. The radioactive decay creating these isotopic records is irreversible. Daughter isotopes don't spontaneously transform back into parent isotopes, don't reset the clock and make rocks appear younger. The isotopic records in rocks are temporal archives, preserving chronological information about formation history in ratios that change predictably and irreversibly with time's passage. Trees grow by adding rings, one per year, creating concentric circles of wood that preserve a record of growth conditions. Wide rings indicate favorable years with abundant water and warmth. Narrow rings indicate stress from drought or cold. The sequence of rings provides a chronological record extending back as far as the tree has lived, and for some species like bristlecone pines, that can be thousands of years. Similarly, ice cores drilled from glacier and ice sheets preserve annual layers of snowfall, each layer capturing a snapshot of atmospheric conditions when it formed. Tiny bubbles trapped in the ice contain samples of ancient air. Dust and chemicals record volcanic eruptions and changes in atmospheric composition. These layers stack forward in time, newest on top, oldest at the bottom. Tree rings and ice cores don't form backward. Trees don't remove rings. Glacier don't layer themselves. The layering is directional, accumulating forward, building records that allow scientists to reconstruct past climates and environmental conditions by reading the chronological archive preserved in wood and ice. Probability theory describes how systems evolve when governed by random processes, and it shows a characteristic tendency called probability diffusion. If you start with a sharp probability distribution, concentrated around a specific state, random processes tend to broaden that distribution, spreading probability across more states, moving the system toward equilibrium. This diffusion is directional. Probability distributions spread from narrow to broad, from concentrated to dispersed, from ordered to random. They don't spontaneously sharpen, don't concentrate themselves without external intervention. Imagine tracking a particle undergoing random motion. Its probability distribution starts concentrated at its initial position. As time passes and the particle moves randomly, the probability distribution spreads, indicating growing uncertainty about the particle's location. This spreading, this diffusion of probability, mirrors entropy growth. Both move from concentrated to dispersed, from certain to uncertain, from organized to disordered. Probability diffusion moves systems toward equilibrium states where all accessible configurations are equally likely, and this movement is inherently directional, following time's arrow from special initial conditions toward generic equilibrium states. Mathematics provides functions that only increase or only decrease, never reversing their trend. These monotonic functions mirror entropy growth in isolated systems. Just as entropy can stay constant or increase but never decrease, a monotonic increasing function can stay flat or rise but never fall. The mathematical structure of monotonicity captures the essence of irreversibility. When physical quantities behave monotonically, always changing in the same direction or not at all, they provide clear markers of time's passage. Entropy is the most important monotonic quantity in physics, but others exist. The scale factor of the universe increases monotonically in our expanding cosmos. The amount of information that has crossed a black hole's event horizon increases monotonically. Radioactive decay proceeds monotonically toward stable isotopes. These monotonic functions are mathematical expressions of time's arrow, quantities that change irreversibly, providing unambiguous indicators of temporal direction. When you measure a monotonic quantity, you can determine which direction is forward and which is backward simply by seeing which way the quantity changes. Monotonicity is irreversibility expressed mathematically. In all of scientific history, across every field and discipline, no observation has ever contradicted the forward direction of macroscopic time. Not once. Not in chemistry labs where countless reactions have been studied. Not in biological observations spanning from molecular to ecological scales. Not in geological records extending billions of years into the past. Not in astronomical observations reaching across cosmic distances. Not in physics experiments probing from the largest scales to the smallest. Every measurement, every experiment, every observation confirms that macroscopic processes evolve forward from lower to higher entropy, from past to future, from cause to effect. There are no authenticated cases of time-reversed macroscopic processes. No broken glasses have spontaneously reassembled. No scrambled eggs have unscrambled themselves. No elderly people have grown younger. The consistency of this evidence across all domains of science is extraordinary and deeply significant. It means that time's forward direction is not a convention or perspective but an objective feature of physical reality, confirmed by every observation ever made. And so we arrive at the conclusion that all empirical evidence supports. We live in a one-way temporal universe. Time flows forward, from the Big Bang's low entropy beginning toward an uncertain high entropy future. This directionality manifests at every scale, in every process, through every force. From the quantum realm of particle decays to the cosmic realm of universal expansion, from the thermodynamic spreading of heat to the gravitational collapse of structure, from the biological accumulation of damage to the geological layering of rock and ice, everything points the same direction. The arrows align. Thermodynamic, cosmological, electromagnetic, quantum, psychological, biological, all pointing forward, all confirming that past and future play fundamentally different roles in the structure of reality. We cannot visit yesterday any more than we can unbreak a glass without external intervention. We cannot reverse entropy's growth any more than we can make heat spontaneously flow from cold to hot. We are carried forward on time's current, moving inexorably from what was toward what will be, from memory toward mystery, from the determined past into the open future. Time moves forward because that is the only direction it can move, the only direction consistent with the laws of physics and the boundary conditions of our universe. And in that forward motion, in that irreversible flow from order toward disorder, lies the explanation for why we experience time as we do, why cause precedes effect, why we remember yesterday but not tomorrow, why the arrow of time points unwaveringly toward the future, never wavering, never reversing, carrying us forward through each moment toward whatever lies ahead in the endless unfolding of cosmic evolution.